For decades, theoretical physics has been paralyzed by a central contradiction. General relativity describes a smooth, continuous spacetime, while quantum mechanics demands a jagged, probabilistic subatomic reality. Every attempt to unify them has hit a mathematical wall. These modern paradigms rely on abstract dualities, curved empty geometries that dictate gravity, and invisible probabilistic fields that dictate matter. Neither provides a physical, deterministic substance for the vacuum. A 2026 paper by independent researcher Menelaos Georgiadis proposes a radical pivot. The elastic continuum theory discards a century of abstract geometry and returns physics entirely to classical continuum mechanics. This framework replaces the empty void with the plenum, an infinite, physical, hyper-elastic solid medium. When the universe is treated as a solid block, the propagation of light, the generation of quantized mass, and the metrics of spacetime emerge from the thermodynamic properties of a single, continuous four-vector displacement field. To prove this mathematically, the theory grounds itself in the principle of least action, applied directly to the displacement of this elastic field. The baseline Lagrangian equation divides into two opposing forces. The kinetic term dictates wave propagation, where transverse oscillation of the vacuum lattice constitutes light. The opposing potential term introduces a periodic sine-Gordon function, dictating how the medium deforms against its internal tension. This nonlinear sine-Gordon potential acts as the mathematical engine of the theory, forcing a continuous elastic block to generate discrete physical reality. This raises the question of how a continuous elastic field creates the discrete fundamental particles observed in the standard model. Because the sine-Gordon potential is periodic, the vacuum cannot remain stable in arbitrary states of deformation. It settles into distinct, stable equilibrium valleys. The continuous field knots itself into these stable positions, creating topological solitons. The math classifies these distinct knots using a conserved invariant known as a winding number. This chart visualizes the topological mechanism. The top graph shows a displacement vector transitioning from negative to positive 1. This spatial gradient traps massive elastic energy, creating the bottom graph's localized density spike. This energy peak represents rest mass, the total work required to deform the vacuum. Matter exists as a dynamic topological knot woven directly out of the continuous fabric of the plenum. This model must resolve a mechanical paradox. How can discrete particles move through a solid block of elastic material? A particle is a geometric state of the lattice. Solitonic motion is the continuous folding and unfolding of that state as it translates through space. At the leading edge of the moving soliton, the lattice deforms and absorbs energy. Simultaneously, the trailing edge relaxes back to baseline and releases its stored elastic strain. In an ideal medium, this results in a perfect zero-sum energy transfer. This mechanical recycling of elastic strain provides the physical origin of inertia and Newton's first law. This graph details the approach of two topological knots. The top chart shows their displacement fields interacting. The bottom chart demonstrates this overlap creates continuous elastic tension between nodes. The vacuum pulls on itself to minimize strain energy, generating what we measure as force. This suggests that localized elastic dynamics generate both near-field nuclear interactions and long-range gravitational compliance without the need for exchange bosons. To model a realistic universe, the theory incorporates internal thermodynamics, adding viscous damping, or friction, into the master equation. Extreme elastic stress alters the refractive index of the vacuum. Mechanical waves propagating through this strained area follow an effective acoustic metric. The physical density gradients of the medium mimic the mathematical effects of Riemannian spacetime curvature, casting general relativity as an emergent effect of continuum mechanics. In this model, time functions as a scalar index for measurement, rather than a physical dimension. Relativistic time dilation is physically reinterpreted as chronoelastic hysteresis, the mechanical drag encountered by atoms moving through a viscous medium. The top chart tracks an atomic oscillator's resonant frequency. An acceleration shock at 5 seconds causes an immediate frequency drop, representing the lattice's physical resistance. As the bottom graph shows, This hysteresis loop creates a permanent accumulated phase deficit. The clock physically ticked fewer times. Human observers misinterpret this physical slowing of local processes as the literal stretching of a temporal dimension. Any unified field theory must seamlessly recover the verified laws of physics as limits of its own mechanics. By enforcing the incompressibility gauge on the master equation, the theory restricts wave propagation within the medium to transverse shear strains. This physical limitation leads directly to Maxwell's equations. Classical electromagnetism emerges as a simple geometric identity of those transverse strains. Moving to quantum mechanics, the math extracts the antisymmetric rotational component of the elastic strain. Mapping this topological torsion using Clifford algebra addresses fermionic spin 1/2. The Dirac equation becomes the macroscopic equation of motion for a chirally twisted vortex propagating through the solid vacuum. These derivations suggest that the seemingly disconnected fields of modern physics are localized, macroscopic limits of a singular thermodynamic machine. Unlike mathematically elegant paradigms that remain difficult to test, the elastic continuum theory subjects itself to strict physical falsification. Under the extreme conditions of gravitational collapse, the restoring force of the Sine-Gordon potential becomes highly nonlinear. The solid vacuum triggers a mechanism called asymptotic hardening. As the strain approaches a critical threshold, the effective elastic modulus diverges, and the lattice physically resists infinite compression. This provides a mathematical resolution to black hole singularities. The core remains a stable topological knot sitting at the maximum allowable elastic strain of the medium, rather than a point of infinite density. This resistance leads to a specific, testable prediction. Light passing near a Schwarzschild radius should exhibit measurable deviations in its deflection angle compared to the calculations of general relativity. Theoretical physics faces a choice between maintaining the geometric abstractions of general relativity or pursuing the mechanical implications of a solid vacuum. Decoding these mechanics suggests a universe that behaves not as a mathematical probability, but as a physical deterministic plenum.